this is the control block diagram for the AC to DC converter. We have completed last class. Here we have put VR, there is a change here. This is VR has to be positive here, here it is to be minus. Why? From our front end converter, the VR is the fundamental between A to B. So, if you see here, VR is equal to Vs plus L di by dt. So, to find out L di by dt, it should be VR minus Vs. So, this is the one it is represented here. So, it has to be plus here and minus here. Okay. Now, how to find out the controller? You have to find out the controller, then PWM converter, how to represent, so that we can choose the controller such a way we get a very good response. That means, for any change in the input, the feedback current will follow it as quickly as possible. So, converter, what we told, it is a sine triangle converter. So, let us go to the next page. This is the triangle signal, and we are comparing this one with a sine wave. So, the comparison is based, that is this Vm. The triangle wave is fixed and Vm is coming from the, Vm is our present VRT reference. So, this VRT is coming from our control signal. Okay. So, that will decide, that will control our converter. So, for instantaneous control, the control should be as fast as possible. The triangle waveform should be triangle frequency, that is the frequency of the triangle waveform FR should be very high compared to FR. Okay, that is one thing, but here this is not true. There is always a delay in control. That means, the once a comparison happen here, the next comparison happening here. So, we have a delay of TR. We have a delay of TR in control. So, this in control we can approximately model as a first order lag. That means, a delay, we are initiating a control action here, but the action happens somewhere here with a delay of TR. So, this we approximately can be modeled as a first order lag. So, first order lag means the time constant, the representation, input output representation is 1 by 1 plus STR. Okay. So, TR is the this period, one triangle period TR. Okay. Now, converter, if you see go to the previous slide, see there is a VR reference and VR. VR is the actual VR. Okay. And VR is the reference value from the control signal, that is this one. So, there is a gain when you make the model here PWM, when you give sine triangle comparison, the sine triangles are done in our analog control signal level or digital DSP signal level. So, VR will not go more than 0 to 5 volt or 0 to 10 volts. And the VR depends on the actual output. So, there is a gain. So, the converter has to be represented as like this. You have to include this gain also into in this one. That is that gain G. Okay. Maybe when we come to the model, before the simulating model we will try out, there we will say what is the. So, converter can be represented, this is the converter, PWM converter we are representing. PWM converter. Now, let us first go back to the inner current loop, that is you have the current reference this is multiplied by sine omega t, which is this sine omega t is which is in phase with the VST, this VST. So, here this one, let us draw the current loop first. So, the current loop you have the current reference, multiplication is instantaneous. So, we will not bring that one will not bring it here, only the delay elements will bring it here. Then you have the plus minus, this is the feedback. Okay. This is our controller. Okay. This controller output will be going to our converter. Converter we are representing it with a gain G and a first order lag, that is 1 plus STR. Okay. This is our VR reference. Then here this minus, this is the actual VR, minus the source minus VR integral the current integral of this difference gives the current. But this the controller we are trying to control with the input as IST star, that is this one. So, this will assume as a disturbance input and we will not take in this control loop here for. Because our controller we are defining with, we are going to design with respect to any variation in our reference IST star. So, differentiation 1 by SL. Then this is the actual converter current. We tap this current through some current transformers or other current sensors and we will put a gain of Ki. So, we have to bring it to the controller level. So, gain will be. So, this is the control loop. How to this is our actual IST source current. So, how to design our controller? See, if you controller, we have studied about many controllers like P controller, I controller, PI controller. So, which one to use here? To start with, we start from the basic, we start some of the idea from the basics of control system. So, let us take, we know the PI controller, the steady state R is equal to 0. So, what do you mean by PI controller steady state R is 0? Let us take let us study a little bit more about PI and PI, even though you know about in your studied about in your control course, just for continuity. Let us take, there is a reference input R. Okay. This reference input, there is a feedback. Let us take a P controller with a gain of K1. Controller part we are using K1, that is this one, K1. Now, this converter, again let us make some system with a first order lag. Okay. First order lag, I will put us with a gain K2 by 1 plus ST, some time constant, with the unity feedback. This is our output. Output I will represent as C. See, we will make our controller, our system very simple. So, this comes here. Okay. Now, let us find out how we design our K1 for a system like this. Let us take CS output. all in Laplace domain, Cs by Rs. See, this is, we know it for a system, open loop gain by 1 plus open loop plus loop 1 plus open loop gain plus feedback loop gain. So, that is, we know it, Gs by open loop gain by 1 plus Gs Hs. So, Hs is unity here, Gs is equal to, so this we can write as K1 K2 divided by, if you do this one, this whole thing will come to 1 plus St plus K1 K2. That is, if you find out the transfer function output by input. Okay. Now, what is Cs by Es, that is error here. See, for ideal control, input should be always tracking the, or output should be always tracking the input, and this here, the signal here, E of S should be 0. So, let us take Es plus Cs by Es, that is, let us take Cs by Es. This will be equal to K1 K2 by 1 plus St. Okay. Now, what is Es by Rs? Es by Rs is equal to Es by Cs into Cs by Rs. Okay. So, Es by Cs we know it, this one by this one. So, finally, this will be equal to, using this one, this equation and this equation. We can find out this part. This will be equal to 1 plus St by 1 plus St plus K1 K2. Maybe I will rewrite here. This will be equal to 1 plus St divided by 1 plus St plus K1 K2. Okay. So, for an input of Rs, the steady state error, that is Es is equal to 1 plus St divided by 1 plus Ts, okay, St plus K1 K2 into Rs. Okay. This one we can again simplify in a better way. We can write it like this: Es is equal to 1 plus St divided by 1 plus St plus K1 K2 into Rs. This again we can simplify as in a simpler form, is equal to 1 by 1 plus K1 K2 by 1 plus St into Rs. Suppose Rs is a unit step input, it is like this. This is Es. Now, we know that the steady state error should be 0. If you have chosen the right controller, steady state, here we are use a proportional controller, and let us see whether the steady state error is equal to 0. Again, from the basics of control system, the steady state error, how do you find out? Limit S tending to 0, SES, what it will be? Limit S tending to 0, SES. For a unit step input, U by US is equal to some value U by S. So, again multiplied by S, these two will get cancelled. Finally, the output will be U by 1 plus K1 K2. Now, if you here for steady state error to be 0, the steady state error is not 0. There is a steady state error when we use this one with a first order plant. Okay, steady state error is equal to there is a steady state error. Now, to make this steady state error 0, let us go back to the previous one. The steady state error, if you want to make it 0, see, only K1 is in our control. This K1, this is the plant gain, that is not in our control. So, to make the steady state error 0, here this value K1 should be very high, such that K1 plus K2 is U by 1 plus K1 1 plus K1 plus K1 K2 should be equal to U by K1 K2 and if K1 is very high, then U divided by K1 will be approximately equal to, it will be close to 0. So, for this, so with the P controller, to make the steady state error 0, K1 should be very high, very high. See, this may not be feasible in many applications. K1, there is always a controller amplitude limit will be there. K1 we cannot have any value. So, with the proportional controller there is always a steady state error. So, we will not be using in this case, but okay, this is one case, and some case proportional controller is sufficient to make the 0 for a system. So, now we are going to study PI for control of a first order plant. So, here a steady state error can happen unless K1 is very high. Now, let us take an integral controller. Integral controller is the transfer function. Let us take in analog domain integral controller will be something like this. Okay. This is our V in, okay, this is our Vf R1. So, we know it, this is V0 is equal to minus 1 by R1 Cf integral V in dt. Okay. So, the output by input in Laplace domain V0 by V in is equal to minus 1 by Rn Cf into S. This is equal to minus 1 by T, Rf I will take a T1 into S. Okay. So, if we use an integral controller, let us take again a first order plant. This is Rs so integral with a gain we can put it. So, K1 by this K1 by S. This K1 is equal to 1 by Ti here. So, this K1 is equal to 1 by Ti. Okay, forget about the negative side, that we can correct it with another inverting amplifier here. So, K1 is equal to 1 by Ti. So, integral representation is K1 by S. Again, let us take a first order plant. K2 by 1 plus St. So, we are giving feedback here. Same like before, if you use the transfer function Es by Rs, this is Es. Same way if you do it, Es by Rs or Es is equal to S into 1 plus St divided by S square T plus S plus K1 K2 into Rs. Rs, let us, if it is a unit step, it will be U by S. Now, again steady state error. Limit S tending to 0, SES, okay, will be equal to, here if you see S square, numerator S square into 1 plus St happens, then denominator will be T into S square plus S plus K1 K2 and the U by S. So, this S goes, denominator always there is an S. So, S tending to 0, steady state error will be 0 here. So, for this controller, the steady state error is always 0, okay. But there is a disadvantage with this one. Sometimes it can create problem. When? See, we have only talked about the first order plant. So, first order plant, if you see here, there is signal coming here, signal come to the feedback. So, it is going through first order lag. So, any sinusoidal signal. So, if you consider Rs contains various signal, it can be split into various frequency components. So, some frequency component, some variations. So, Rs with some frequency variation, it can give a phase delay here also. So, if this integrator, what is the phase delay of this integrator? If you draw the plot of gain versus frequency plot of integral controller, it will be gain versus omega will be something like this, okay. This will be at 1 by T1, the integral time constant. So, here it will be 0, this will go with minus 20 dB per decade. So, according to control system this is good, but let us take the phase margin, this will always give a 90-degree phase shift, fixed 90-degree phase shift to the signal. So, if the controller, if the plant has some other frequency dependent element and force signal, if we again give a minus 90 degree, so minus 90 plus minus 90 it will be minus 180. So, the negative feedback can sometimes become positive. So, it is not always preferred, that also depends on the controller. So, the controller selection depends on the plant and its transfer function, and again with the controller transfer function, with the controller transfer into closed loop transfer function, how it behaves. So, let us take PI controller. So, what we want, a controller where we should have large gain should be possible for steady state error. That means steady state error means for DC component we should have very large gain At the same time, we should be able to fix the margin at this 0 crossover period. 0 crossover period where the gain is will be 1 when the log scale. So, let us talk about the PI controller now. See, PI controller, see if you want to use it with an operation amplifier, it will be schematic representation will be like this. Okay. This is our V in. So, here let us this be R1, RF and CF. So, here V0 S divided by VIS is equal to RF by R1 plus 1 by R1 CFS. So, the overall transfer function will be RF by R1 if we take as some K, overall transfer function will be K into 1 plus RF CFS divided by RF CFS. Okay. This is of the form K into 1 plus ST by ST. So, if you see here, it has the integrating part here. Then, if in the pole 0 form, there is a 0 at here also. So, how the frequency response for the PI controller here? Let me remove this one. PI controller, okay, I can draw the PI controller here. The PI controller will be, I will draw with a different color. So, gain will be, so if the gain versus frequency, you have the very high gain at 0 frequency side, because 0 frequency S equal to 0, it will be very high. S is equal to 0 means the gain will be very high, infinity. So, the ideal concept of infinite gain or very high DC gain is possible. Same like our PI controller. So, steady state error is possible, and at the same time we can also control the phase shift by choosing the T here. So, here if you see here, it will come here, then when it comes to at 1 by T, that frequency, the 1 by ST zeros effect will come into picture and it will go like this something. So, the phase margin if you see here, this because of the integrating it will start from minus 90 degree and slowly it will go to 0 here. So, by placing this one overall in the overall closed loop control, the phase margin at the 0 at the gain crossover we can adjust it. So, both the gain as well as the phase shift we can control. So, this will also have the steady state error, 0 steady state error because of the integrating element here. Now, because of the integrating element here, that is this one, because of this one 0 steady state error will be here. Now, let us use a PI controller for our current loop transfer function and let us study how it works. So, if you see here, this is our current loop. Now, in this controller part, here we will use a PI controller. Let us study the effect of PI controller here. IST reference here. This PI controller. So, transfer function will represent as K into 1 plus ST1 by ST1 into G by 1 plus STR. This is our converter then 1 by SL, this gives our actual current, which will sense and bring to the controller level. So, it will be like this. Now, let us take the transfer function IST by output by input, that is IST by IS star T, GS HS by this open loop gain and the closed loop gain, GS by 1 plus GS HS. If you do, it will be equal to K into 1 plus ST1 by ST1 into G by 1 plus STR into 1 by SL divided by 1 plus K into 1 plus ST1 divided by ST1 into G by 1 plus STR and K by SL. Okay. So, if you see, the moment PI controller is added, there is a, we are introducing a pole. So, here instead of K, we will make it Ki, that is the current feedback gain. So, this is Ki. So, we are giving a 0 here. So, the moment give the 0 means it can give large overshoot. So, the giving a 0 means you are giving a phase lead. So, it can give large overshoot. And also the purpose of PI controller, this is introduced such that T1 we can choose it, such that we choose T1 such that a dominant lag element here. So, the moment you have the converter this type of 1 plus STR, it will give a delay. So, this delay can be cancelled by this one. So, the response can be faster. So, let us make T1 is equal to TR. So, that the large lag element, delay element due to this converter 1 plus STR can be cancelled by this lead element from our PI control. So, let us take T1 is equal to TR. If you use it, we can cancel these two. Okay. So, system become simpler. But let us see the final transfer function. If you take it, it will be S square LT1 kg divided by S square LT1 plus kg ki, this is the denominator. So, if you see here, see this S square Li here, here also S square T1 LV is there, S square T1 L. So, this will get cancelled. So, finally, the transfer function becomes kg by S square L T1 plus kg ki. If you see here, any response of the system for any unit step input here, Is, depends on the denominator. In the denominator, the moment you use PI control and pole 0 cancellation, the first order term is missing. That is, the damping factor is missing and the system becomes oscillatory. So, what I want to say here, just like that we cannot use the PI controller, everything depends on the plant transfer function. Now, but this is the whole thing is coming from our converter model. This is only in our controller. So, how we will be able to choose our controller now? PI controller is not possible. Let us take our, so we have to choose a controller in such a way, whenever there is a variation in the input, output should follow instantaneously. That means, if I have a variation like this, output cannot see if I want to have a variation like this, sorry, output cannot follow exactly like this. So, step input is not possible. As possible, it can have a first order. That is the most first order way of changing it with a time constant, with a small time constant. So, we want the response to follow as a first order lag for any change in current. So, let us take the time constant for the first order lag. Let us see how to find out that one. So, let us take the general nature. If for any change in the reference, the feedback current should be vary as a first order lag. So, if you first order lag, if you write down the differential equation, it will be T rate of change, our feedback current, dt plus ist is equal to our is star t by ki. What it shows, in our previous current control loop, the whole transfer function, by putting the controller here, the whole thing with the feedback should behave like a first order lag. That means output by input. If you go back to here, the transfer function will be ist into 1 plus st is equal to is star t divided by ki. That means the output with respect to input will be ISR t divided by ki into 1 by 1 plus st. That means for any change in ISRT, IST will be IST, that is the feedback current. So, that means feedback current means that gain factor IS ki into IST will, the change variation will be IST will be as a in the form of first order lag. So, we want the current reference or current feedback to follow the reference with a first order lag, and the time constant, let the time constant be t. The step change may not be possible. The next optimum way of change is the first order lag. So, t into das by dt. So, if you see here in Laplace domain, it will be is into 1 plus st into is star divided by ki. That means ki into is, it is a function of it is a Laplace function, is equal to is star into 1 by 1 plus st. Ki we take it and bring it here. So, this will be the first order lag. Now, let us take from the first equation here, what is the rate of change for this type of response? What is the rate of change we want? Rate of change we want is equal to dist with respect to time by dt is equal to is star t minus ist, is star d divided by ki, that gain function. Okay? This is the change we want. From the converter, if you see here, see the source voltage Vst plus L di by dt is equal to Vrt. Okay. So, dist by dt is equal to Vst minus Vrt divided by L. Okay. This is what is happening in the converter, and this is the response we want, dist by dt. So, from this, okay, here one t is missing, we have to take t into dis by dt. Okay. So, equating these two equations, that is this one with respect to this one, this equation is what is actually happening in the converter, So, VRT is the actual VRT, but what we want is the VRT star for a first order response. So, let us introduce this, equate these two equations, introducing VRT star. So, VRT star is equal according to a converter with a gain G. Okay. So, G into VRT star minus VST divided by L is equal to 1 by Ki into T into IS star, that is a reference, minus the feedback with a gain reduction from the converter loop. This is the one. From this one we can find out what is VR star T. T is equal to L by Ki GT into ISR T minus IST into Ki. Okay. So, to get the VRT star, we have to put this gain element LGIPT here in the closed loop controller. That means, if you go back the controller here, instead of PI controller, here, we have to put a proportional controller here. That is equal to, that proportional controller is equal to L by Ki, that is a current gain in this K, then the converter gain G into T. T is the time constant, first order time constant, what we want. Now, let us, from this converter, what we have to find out, whether the system is stable, and for that stable condition, what is the T required. Okay. So, let us write down the IS by IS star T here. Our input IST star, okay, controller here, it is L by Ki G into T. Here we will get the VRT reference, G by 1 plus STR, TR is the triangular period TR, then 1 by SLS, sorry, SL only we are using, sorry, 1 by SL, this is our IST, this is our Ki, we will give it here. Okay. Now, let us find out what is the transfer function here, input output, that is IST divided by ISRT. This is equal to L by KIGT, that is again, into G by 1 plus STR, that is the forward gain divided by the closed loop gain, into 1 by SL divided by 1 plus L by Ki GT G by 1 plus STR and Ki divided by Sn. Okay. So, this we can simplify, again taking this one to this side in a proper form, it will be 1 by Ki, this you can easily do it by 1 plus St plus S square T Tr. So, if you see here, compared to the previous PI controller, here the second order and first order term is there. So, it has the damping factor here. So, system will be stable. Now, we have to choose T such that we should have a optimum response. So, in control system, we know it for a transfer function of the form like this. So, this also we can write in a different form like this, that is 1 by Ki divided by S square plus 1 by TRS plus 1 by TTR, we can write it. This is of the form omega n square by S square plus 2 theta omega ns plus omega n square. Okay. So, it is being a second order, the response is like a second order. Now, for a second order system, for a good response, we know the damping theta should be equal to 0.707 is equal to 1 by root 2. So, let us substitute this one here and find out what is the T required, so that we will get a good response based on the damping here, theta is 0.7. So, if you go there, the omega n square equating the previous value will be 1 by T Tr, then 2 theta omega n is equal to 1 by Tr, and the theta is equal to root T by 2 root Tr, that is, now theta is equal to 1 by root 2. That means 1 by root 2 is equal to root 2 divided by 2 into root Tr. This implies T is equal to 2 Tr. So, if you put T is equal to 2 Tr, you will get a good response according to the response for a good response based on a class convention based on our control system point of view with the theta is equal to root 2. So, we can use that one. Now, see this current loop in the closed loop control system, we have outside voltage loop, inside current loop, and current loop, inner current loop should be fast acting compared to the voltage control, then only voltage control will be pakka. Because any change in voltage happens because of the mismatch in the load current and current control. So, current loop should act very fast. That means the response, frequency response of the current loop should be much higher than the outside voltage loop. So, let us put T into 2R, put this into the current loop and then find out what is the controller required for the output voltage loop in the next class.